this is going to be the final lecture on the crystal symmetry part of this course. So, before I just get into what we are going to do in this lecture is have another look at the international tables for crystallography, volume A, which we had seen earlier when we were discussing plane groups. Now, now I want to look at the international tables for crystallography from the point of view of three-dimensional space groups. But just before I get into this, I want to kind of summarize what we had done in the last couple of lectures. So, glide planes we had done in quite some detail, and we had also discussed screw axis. But in the previous lectures, I did not discuss the six-fold screw axis. So, let me just kind of summarize what are all the possible screw axes that can be present in the space groups. So, in the case of screw axis, we can say in general, we can write a screw axis like n subscript m, where m is less than n. So, m can take up value from 1, 2, 3 till n minus 1. So, if I had let us say a two-fold screw axis, then m can take up only one value, which is 1. If I have a three-fold screw axis, then m can take values 1 as well as 2 and so on. So, what are the operations of a screw axis? So, the operations of a screw axis is first rotation by 2 pi upon n, followed by a screw translation vector tau, which is m divided by n times the translation vector along the screw direction or along the screw axis. So, translation, and this is a lattice translation along screw axis. So, if I had, for example, if I had a screw axis like 2 sub 1, then basically we are looking at a rotation of pi followed by, so I can write it like this, pi followed by tau, and in this case tau would be half the lattice translation. So, m would be 1 and n is 2. If I had let us say 3 sub 2 screw axis, then I will have a rotation of 2 pi by 3 or 120 degrees followed by the screw translation tau, and in this case tau would be equal to 2 upon 3 times the lattice translation. So, this we have already discussed. So, this is just a summary of what we had done. Now, let me just list down all the possible crystallographic screw axes. So, the various screw axes. So, first let me start with just a pure rotation axis, two-fold rotation axis, and its graphical symbol is an ellipse. The screw axis, two-fold screw axis 2 sub 1 will have a symbol like this, where essentially it is again a kind of an ellipse, but there are two fins coming out from either end to show that this is a two-fold screw axis. Then we have a pure three-fold. This is represented by a triangle. Now, 3 sub 1, we draw a triangle and then we extend fins in this manner. 3 sub 2 start again with the triangle, but the fins are extended in the opposite direction. So, this is 3 sub 2. Now, consider pure 4-fold. So, that the graphical symbol is a square. 4 sub 1, we start out with a square and then we extend the fins just like we did in the case of 3-fold. Four sub 2, then I also have in this case 4 sub 3. So, let me first draw 4 sub 3. What is the graphical symbol for that? So, the fins will be extended in the opposite direction as opposed to 4 sub 1. So, we have a symbol like this. Now, coming to 4 sub 2, we start out with a square and there will only be 2 fins, one at the bottom here and one at the top out here. Now, 4 sub 2 also has as a subset a pure 2-fold rotation symmetry, and therefore, the graphical symbol also represents that the symbol itself has the pure 2-fold rotation. Then now coming to 6-fold, now how many screw axes we are going to have in the 6-fold? Well, as we said, in general the screw axis is n sub m, where m can take up values from 1 to n minus 1. In this case, the m, the subscript, can take up values from 1 to 5. So, there should be total of 5 6-fold screw axes. So, starting out with a pure 6-fold rotation, we have an hexagon as a graphical symbol. 6 sub 1, start out with the hexagon and extend the fins in this manner. Six sub 2, then I have 6 sub 3, I have 6 sub 4 and 6 sub 5. So, we have drawn the graphical symbol for 6 sub 1. Now, look at 6 sub 5. 6 sub 5, the fins will be in the opposite direction as opposed to 6 sub 1. So, this becomes the, if you compare the graphical symbol for 6 sub 1 and 6 sub 5, you can see that the fins are drawn in the opposite direction. Now, let us consider 6 sub 2. 6 sub 2, starting out with the hexagon, and we will have 3 fins in this. Now, this is in fact, the symbol itself clearly shows that this has a pure 3-fold rotation as a subset of the 6-fold 6 sub 2 screw axis. And if I look at 6 sub 4, 6 sub 4 also has a pure 3-fold rotation, but comparing it to 6 sub 2 and 6 sub 4, the fins will be drawn in the opposite direction. And this again you can clearly see has a pure 3-fold rotation. Now, coming to 6 sub 3. So, 6 sub 3 again start out with the hexagon and it will have essentially only 2 fins, also showing that the subset for 6 sub 3 is a pure 2-fold rotation as well. So, this kind of summarizes all the screw axes, all the crystallographic screw axes that are possible. Now, with this, let us now come to the international tables. So, international tables for crystallography volume A that we have already seen in the case of plane groups. Now, let us just take a very few examples of international tables for crystallography, a few space groups. So, taking the first example, the C121 space group. So, C is standing for end centered. There is a two-fold rotation. So, the combined together, one should realize that this belongs to the monoclinic crystal system, and it is an end centered monoclinic with the C face as the centering face, while the unique axis is B. We have already discussed this. So, now we are just looking at the international tables. So, unique axis is B. So, if you look at this diagram, we have a base as the parallelogram here, or rather it is a AC face, and B axis is perpendicular to the AC face, and basically where the two-fold rotational symmetry is there. So, there is a two-fold out here, and then the two folds get populated to the corners, and you also get them at the edge centers. Now, if I had put a motif out here above the plane, 180-degree rotation will bring it here, and it will still remain above the plane, no change in handedness, and all of these get translated through lattice translation. And there is another lattice translation as well, which is to the centered lattice point on the C face, or rather we can say on the AB face. So, B axis is perpendicular to the diagram. So, you can see that this AB face is going to be perpendicular to the figure. So, it is essentially going to be the centering translation is going to be half A plus half B plus 0 times C. So, if I look at this centering translation, these two motifs get translated to half plus position. So, you will have here, and you will also have motifs drawn out here. Essentially, what I have drawn here is identical to what is already present in this fourth diagram that you see in this, where only the motifs are shown. So, in this we also saw that if I have to go from, so if this was 1, 2 and this became 3, then going from 1 to 3 will be through a screw axis out here, and in this manner you get these screw axes at different locations. Now, this diagram essentially has been drawn when the projection, so it is a projected diagram, so projection along the unique axis, along the B axis. So, projection is along B axis. This diagram, for example, is different. In this diagram, we are showing that the projection is along the A axis. So, if you think about it, so now we are projecting along the A axis, so it is a rectangular face that is getting projected, which is essentially nothing but the BC, and this is B sub P. So, it is a projected C axis and the B axis, and the origin is out here. Now, what happens in this case is that the two folds, all the two folds along, if you notice along the A axis on this diagram, they all line up and they get projected on top of each other, the two folds and the two fold screw axis as well. That is shown by this, by an arrow. Let me just draw this again so that this becomes clear. So, essentially it is showing that I have a two fold getting projected onto the same line, the two screw axes are getting projected on the same line, shown by half an arrow, indicating that these are two fold screw axes. Same way, same symbol out here, same symbol out here, these are all the same symbols. Here, in this case, the projection is along projection is along C. So, now once a projection is along C, we will be able to see the two folds and the two-fold screw axis separately. So, this is my two-fold, this is 2 sub 1, this is 2, this is 2 sub 1, this is 2. So, they all axes are in the plane of the diagram. So, these are just different perspectives on this. Now, and if we want to see the C2, this is a short form of the symbol. In the list of 230 space groups, this is space group number 5, and the point group associated with it is the point group 2. Okay, here basically is telling me that the origin is on 2. This is the asymmetric unit, where x varies between 0.5, y varies between 0.5, and z varies between 0 and 1. In the case of plane group, the asymmetric unit was an area. In this case, this is a volume element of the in the space group. So, asymmetric unit, if I have to identify, so this it can be written as, this was actually, these two have the same, they have the same axes. So, they have the same axes. So, this is C and this is A. So, if I look at the asymmetric unit, so basically C is along Z. So, Z varies from 0 to 1. A, which is x, varies from 0.5. So, area wise this gets covered, and then 1/2 up along the B axis or along the y axis is the asymmetric unit. So, this is an asymmetric unit with 1/2 up along B. Now, these are the symmetry operations. So, there is a one-fold, identity operation will always be there. Then there is a two-fold, and its location is 0, y, 0. So, essentially what is y? Y is the screw axis, the y is a two-fold rotation axis. So, any point, so any value of y means any point on the two-fold is what this is representing, or we can say the two-fold rotation symmetry basically starting at the origin. Then I have, this is for the lattice point at the face center. So, I have the centering translation, and I have a two-fold rotation symmetry, 0, 1/2, 0 and 1/4 y 0. So, these are the symmetry operations that are present in the cell or in the space group, and then this is something again we had seen in the plane groups, that the generators selected. So, you don't select all the symmetry operations. So, all the translation symmetries, this is along A, this is along B, this is along C, and this is the centering translation, and this number 1 in bracket indicates that it is referring to this particular symmetry, which is in this case identity, and this out here 2 is representing the two-fold at 0, y 0. So, these are all the minimal set of generators required to produce the entire space group. Now, again now we come to the Wyckoff positions, again analogous to what we had seen in the plane groups. So, I have, starting with here, this is the general position, it has a multiplicity of 4. General position means, so basically all of these motifs that you see are representing the general positions. So, this is actually a general position. So, there should be 4 coordinates here, but you see only 2 coordinates. So, we start from x, y, z. When you have a two-fold rotation, the two-fold axis is along y, the unique axis y. So, the other 2 coordinates will change. So, x will go to minus x, z will go to minus z. So, this gives me only 2 coordinates, but I have a multiplicity of 4, there should be 2 more coordinates. So, this is basically, if I look at this, first add 0, 0, 0 to these 2 coordinates, so I will get the same coordinates. Then add half half 0, so I will get the third coordinate as x plus half, y plus half and z, and the fourth coordinate that I will get would be x bar plus half, y plus half plus z bar as the fourth coordinate. So, that is how you get 4 positions, and you can also see that there are 4 general positions. So, this is 1, 2, 3 and 4 inside the unit cell. So, in this general position we could have given coordinates for each of these, but instead of doing this we give coordinates for these 4. So, we have to select some unique set 4. So, we select this 4 for convenience. Now, these are special positions. The side symmetry is 2 in both the cases. One is at 0 y 0. So, it is a two-fold axis coming out at the origin, and 0 y half is a two-fold axis coming out at the center. So, now again you see only the multiplicity is 2 in both the cases, but you only see one coordinate, but the second coordinate you can get by adding half half 0, just like we did in the earlier case. When you add this, so this is half y plus half and 0, this would be half y plus half. No, this one is not 0, y plus half comma half, and this is half y plus half 0. So, these are the various positions for the special position. So, you have only 3 Wyckoff positions for this particular space group. Now, this is again space group that we have already seen, and this is excerpt from the international tables. So, essentially what we have done is take the primitive monoclinic and we have added two-fold screw, and you have glide plane where the glide direction is C. And if I look at this diagram again, the unique axis is B in this case, and the complete symbol is P1 to 1 upon C 1. So, these are the symbols, these are my screw axis and these are my center of inversions. So, this is projection along B. Now, this is projection along A. So, as a result, what we have is, if I look at the glide plane is the AC plane. Now, if I do a projection along A, where this is my origin, this is the B axis and this is the C sub P axis, the projected C axis. So, the glide plane is essentially parallel to the AC plane, and that is why in this figure the glide planes will be perpendicular to the figure. So, the glide planes and the glide direction is along C. So, this is a diagram as projection along C axis. Then you will see that the screw axis and the screw axis you can see by these half arrows representing screw axis, and there is 1/4 written here, which means that screw axis is 1/4 up in this diagram, and this essentially these two have the same axis system. So, this is C, this out here is A, and this is how the general positions move around when you apply the symmetry operations. This is my asymmetric unit, x between 0 and 1, y between 0 and 1/4, and z between 0 and 1. So, this I will leave it to you to figure this out, how the asymmetry unit, which you can do the shading where the asymmetric unit is there. These are the symmetry operations. So, you have identity here, this is twofold and the location, this is inversion symmetry, and this is the C glide. A minimal set required to generate the space group is given by this generators selected. So, these bracketed numbers 1, 2 and 3 are essentially referring to this, the symmetry out here and the symmetries out here. Then these are the Wyckoff positions. So, this is a general position which has a multiplicity of 4, and this is how the general position coordinates move around when you apply the symmetry operations, and these are my special positions. Now, you can see that the special positions are only where the inversion center is. There is no screw axis which is a special position. In fact, even if we see in the earlier case, we do not have any special position on the twofold screw axis, because it does not create a special position because of the screw translation that is involved. And if I even put an atom on a screw axis, I will still have the multiplicity of 4 for the general position. So, an atom placed on a screw axis, or in fact also on a glide plane, which is in this case there is a glide plane as well, you will see that none of them are special positions and they will always have a multiplicity of the general position. This is the P22 space group, and I will here essentially we do not have any unique axis. So, we will just call this as A, this is B, and the C axis is perpendicular, and one can see how the general positions are distributed. We have asymmetric unit, which is this one, the symmetry operations, and we have a very large Wyckoff table now, where there is a large number of special positions. So, these are all special positions. And this one is a general position, and one can study this in detail, and you should have a look at it in detail and look at it that all of these positions are either in the top general position or a special position. And if you look at the Wyckoff letters now, so these are the Wyckoff letters. So, Wyckoff letters A goes from we start just labeling them as A, B, C, D onwards, they go all the way up till U. And you can see that you have multiplicity of 1, where if the special position lies on the intersection of the 3 twofold axes, or you will have special position of 2 if the position is on a twofold axis, and then of course, at a side symmetry of 1, which means no symmetry, you have the general position multiplicity of 4. Now, this one is P4 space group, and you can see here, you can this is my A, this is my B, this is my origin, and this is space group number 99, and this belongs to the tetragonal crystal system. I have asymmetric unit x going from 0 to half, y going from 0 to half, z going from 0 to 1, and x less than or equal to y. Essentially, if I look at how many general positions are there within the cell, so I have 1, 2, 3, 4, 5, 6, 7, 8. So, the volume of the asymmetric unit should be 1/8 the volume of the unit cell. So, and if that is how you will see that there is also a relationship between x and y. So, x is less than or equal to y. If this was not there, then this entire thing would be the asymmetric unit, and with z going from 0 to 1. So, instead of this, what we have as the asymmetric unit is half of this thing. So, this is my asymmetric unit. Then one can look at again quite a few general positions, no, quite a few special positions, and the general position has a multiplicity of 8, and hence you can see that there are 8. If you start with one general position x, y, z, when you apply the symmetry operations, there are 8 positions that are created, and then you have the special position sitting on the intersection of two mirrors and a fourfold will have multiplicity of only 1. Now, coming to P3, so this is a very simple space group, and I only want to point out one thing in this, and that is going to be the asymmetric unit. Now, asymmetric unit looks a bit more complicated here, where x varies from 0 to 2 by 3, y varies from 0 to 2 by 3, z varies from 0 to 1, but then you have a more complicated relationship between x and y. Now, this, if I join, this becomes the asymmetric unit in this case. So, I am trying to point out here that asymmetric unit need not be a rectangle or a square or a triangle, it can be a more complicated shape. You have relatively few special positions in this, and the general position has a multiplicity of 3. So, with this I conclude this lecture, and in the next lecture we will start with the diffraction part of this course. Thank you.